There are at least two common ways to visualize addition, or to see addition. One way is by using counters, such as by using pom-poms. Another way is by using a number line, such as by using rulers. In a previous video, I explained why these methods of seeing addition are basically the same idea, well, at least for positive integers. The link for that video is in the description of this video. We have already used counters to explain for several cases why you add fractions in a certain way of adding the numerators and keeping the denominators the same. The cases in which we did not use counters to explain this rule were when you include a negative denominator or a denominator of 0. Now I'm going to be using a number line to explain why you add fractions in a certain way of adding the numerators and keeping the denominators the same. I'm going to go over one example for each case except for the cases of which you include a negative denominator or a denominator of 0. You may wonder why I have several number lines, several sets of rulers. The reason for this is that I have a different number line for a different denominator. I would also like to show what the number 1 is represented by in each number line. This is 1. This is 1. This is 1. This is 1. And this is 1. Additionally, this is negative 1. This is negative 1. This is negative 1. This is negative 1. And this is negative 1. I would like to note that for these examples, we will be just going over addition. If you wanted to see how you could subtract fractions, simply do the opposite. Well, let's get on with our first example. Suppose I want to solve 3 9ths plus 5 9ths by using a number line, by using rulers. Well, first of all, I'm going to need to have a number line with everything in ninths. And here you go. Then I need to place my marker at 3 9ths. And it is at 1 9th, 2 9ths, 3 9ths. Because of the plus sign and because of the positive 5 9ths, I'm going to need to move this marker 5 9ths steps forward or towards positive infinity. And here we go. 1 9th, 2 9ths, 3 9ths, 4 9ths, 5 9ths. And it landed at 1 9th, 2 9ths, 3 9ths, 4 9ths, 5 9ths, 6 9ths, 7 9ths, 8 9ths. Therefore, 3 9ths plus 5 9ths is equal to 8 9ths. I would like to explain why you add the numerators but keep the denominators the same for this example by comparing and contrasting it to solving 3 plus 5. To solve 3 9ths plus 5 9ths, I get a number line with everything in ninths. For 3 plus 5, there isn't a denominator other than a denominator of 1. All the markings, the main markings are integers. For 3 9ths plus 5 9ths, I move my piece, my marker, to 3 9ths. For 3 plus 5, I move my marker to 3. Because I'm adding and I have a positive 5 9ths, for 3 9ths plus 5 9ths, I will move my marker 5 9ths steps forward. 1 9th, 2 9ths, 3 9ths, 4 9ths, and 5 9ths. For 3 plus 5, I would move my marker 5 steps forward because of the plus sign and because of the positive 5. 1 step, 2 steps, 3 steps, 4 steps, 5 steps. For 3 9ths plus 5 9ths, I see where I land at, and it is at 8 9ths. So therefore 3 9ths plus 5 9ths is equal to 8 9ths. For 3 plus 5, I see where I land at, and it is at 8. So therefore 3 plus 5 is equal to 8. As you might have seen, for both of these examples, we're basically doing the same motion, except for 3 9ths plus 5 9ths, everything is in ninths. Therefore, to solve this problem, you add the numerators but keep the denominators the same. Suppose that I wanted to solve 7/8 plus negative 5/8 by using a number line. Well, first of all, I'm going to need to have a number line with everything in eighths. Then I'm going to need to place my marker at 7/8. And it is at 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8. Because I'm adding negative 5/8, I'm going to need to move my marker backwards. I'm going to need to move it towards negative infinity. The reason for this was explained in the previous set of videos called something like adding and subtracting positive and negative numbers. The link for that set of videos is in the description of this video. Anyway, I'm going to move my marker backwards 5/8 steps. 1/8, 2/8, 3/8, 4/8, 5/8. And where is it at now? 1/8, 2/8. Therefore, 7/8 plus negative 5/8 is equal to 2/8. I would like to explain why you add the numerators but keep the denominators the same when you solve 7/8 plus negative 5/8 by comparing and contrasting it to solving 7 plus negative 5. To solve 7/8 plus negative 5/8, I get a number line with everything in eighths. To solve 7 plus negative 5, all the major markings are integers, like 1, 2, 3, and so on. To solve 7/8 plus negative 5/8, I put my marking at 7/8. For 7 plus negative 5, I put my marking at 7. To add negative 5/8, I move my marking back 5/8. 1/8, 2/8, 3/8, 4/8, and 5/8. To add negative 5, I move my marking back 5 spaces. 1, 2, 3, 4, 5. I land at 2/8 for 7/8 plus negative 5/8. Therefore, 7/8 plus negative 5/8 is equal to 2/8. And I land at 2 for 7 plus negative 5, and therefore 7 plus negative 5 is equal to 2. You may notice that for both of these examples, they are very similar. The only difference is for 7/8 plus negative 5/8, everything was in eighths. Therefore, to solve this problem, add the numerators but keep the denominators the same. The next video in this set of videos has the third, fourth, and fifth example about why you add fractions in a certain way using a number line. If you would like to skip those examples, feel free to click on the second link, which is about the summary, counterexamples, and a thank you.